Hello all, I'm here. Finally, I'm here. So we will have a quick discussion around 4 minutes to six. So and we then start into the our session. Okay. So you just comment in, and I will be seeing, and I will be answering your questions, whatever the comments I will get. Hi guys, is anybody there? Hello, just comment in. We are going to start in about 3 minutes. Yeah, hi. Yes, yes. This is Patrick. Okay, cool. Hi, Sushil Kumar sir. How are you? Okay, we just have 3 minutes to start. Okay. Just start discussion, okay? We can have our own discussion right now. Just start anything. Hi, hi. No, no simple hi. Sir. You can ask, something related to the subject or some session relating to the session. So we just have 1 minute, and yes, I'm going to start at six. Yeah, today's topic is image classification with deep learning. Actually, we are going to discuss on convolutional neural networks, and we take it to the another level, and we are going to use some pre-trained model because it is difficult to train a huge network on our small machines, right? And we will be classifying 101 categories. Yeah, definitely I will be doing some introduction. Not at all a problem. Okay, here we go. Three, two, one. So, okay. Hello all, it's Saidif here. This session is all about image classification with deep learning. Please note that this is my very first YouTube live, and if there anything goes wrong, please excuse me for that. So, And also note that the images used in these presentations are solely taken for educational purposes and it belongs to their own respective owners. So what exactly an image classification and why do we need it? Basically, lots of images are being uploaded to the web every day and we need to analyze them in order to get an optimized solution to any particular problem. So image classification is one problem where another set of problems are built on top of it. So we can build many models on top of image classification, something like image captioning, or many more are there. So let's see what exactly an image classification is. So image classification is a very large field, and with the popularity of deep learning, it's only continuing to grow. So, the primary object of image classification is to interpret the contents of the image and understand the context in image features. Image classification at the very core is the task of assigning labels to an image from a predefined set of categories. So, assigning labels from a predefined set of categories, I mean that if you are going to train our model on cars, I mean different type of cars, something like Mercedes, Audi, some kind of things, then we are going only to classify among them. We are not going to classify between the trucks and the persons. Okay, so we give the whatever we give, and that is what we are going to classify. So that is the thing. And yes, so to give you a simple intuition to image classification, consider the billboards, digital billboards, what you have been seeing on some roads, some digital billboards displaying advertisements, some random advertisements. So it would be better if that billboards display the advertisements regarding to the vehicles that pass by. Something like if there is a Benz car is going on, it would better to display something like a very good, I mean, a car model. So if an school truck, I mean, school van is going on, then definitely it would be carrying the children. Then therefore, it would better advertise something related to children. So how this can be even possible? Well, that can be possible with image classification. So if we introduce a person there, so forget about this image classification, we are going to introduce a person there. Simply we are assigning a person and we are just giving him the control of that billboard. So he has to control that billboard according to the vehicles that are coming in. Therefore therefore he will display the advertisements with respect to the vehicles he sees. Something like if he sees some Audi car, he will display some rich models, something like that. So rich advertisements also like that. So the perception of human is very it is very accurate, but the reaction time for the human is very low compared to computer. So it is better we build a model that behaves as a human, which can classify the things. Something like it can classify between the Audi and the Mercedes, some cars and trucks, some trucks and the motorcycles. Therefore, it just you know uh, optimizes the advertisements for each classes. Something like as we discussed before. Also, yes, it can be used in AI Poly is an iOS application that recognizes the object in real time video and helps the visually impaired people. Yes, it detects the whatever the object they are going to see in particular video of an iPhone, and it just speaks out. Okay, this is a rug, this is a painting, this is a sofa, something like that. Okay. So also, Facebook AI research team has built a deep convolutional neural network to recognize contents in an image. Who knows that one day the Facebook may recommend you people based on the images they share, post, and like. Also, they might use this optimize the advertisements for an individual. Suppose you like a post or share the images of fashion, then you will be getting advertisements based on your choices. Something like denims, sunglasses, something like that. Okay. Okay. So in order to build an image classification engine, we will be using convolutional neural networks. Let's get a quick refresher into convolutional neural networks. So convolutional neural networks involves several layers like convolution, activation, and pooling. Convolution is the process of adding each element of the image to its local neighbors weighted by kernel or filter. So filter is something you can see here that is very dark at the very bottom. This is what we call a filter or a kernel. So again I am repeating, convolution is just the process of adding each element of an image to its local neighbor. So this element will be added to another element that, but it will be added, I mean weighted by a filter, something like this. Okay. And also, yes, here you can see the yellow one is what we call a filter or a kernel, and the green one is an actual image. Yes. And the output resulting feature map, I mean whatever we get the output here, the right side, is what we call a feature map. The dimension or the shape of the feature map will be the actual shape, I mean the actual shape minus the filter length. So here it is 3 by 3. So the actual image shape is 5. So 5 minus 3 plus 2 into padding, 2 twice the padding. So here we didn't introduce padding. Okay, I will be discussing the padding later, and that will be divided by the total number of strides. Okay, we will be discussing that later, and total we add by 1. Okay, so the yellow one what you are seeing is what we call a filter or a kernel, and each element of an image will be added to its neighbor weighted by the weights introduced in the kernel or the filter. Okay, so padding is some kind of phenomenon, some kind of technique that is used to preserve the length of the image. Sometimes we may need to preserve, the shape of the image to be constant or to be not too short. In there we introduce padding is something like we add some kind of zeros or uh, s- some values, some constant values. Okay. And strides are nothing but the steps we take as we move on to the as we slide on to the convolution network. Okay. Then yes, after this we will be applying activation function. Okay, we will be discussing that later on. And yes, after that we will pool that. Generally max pooling will be used. Max pooling is something, uh, pooling is generally used to downsample the image without losing so much information of an image. Generally max pooling and average pooling are used. uh, the reason max pooling we are using here is because at least I have seen very good results with max pooling rather than in average pooling. So max pooling just means that maximum of whatever we see. Here we can see 1 1 and 5 and 6, and the maximum of all these here 6. So here we introduce, and also note that the we are going with 2 by 2 filter with stride 2. So we are jumping into 2 steps. So this is the step 1 and this is the step 2. So again we will be dealing with here. Again we have 2 steps. So 3 2 1 2, and the maximum is 3. So something like that. So generally, as I have said, the general architecture will be convolution and then followed by some activation function like ReLU or tanh or sigmoid, and then the max pooling. Or it can be also done something like convolution, max pooling, and activation. It is up to your choice. So we can actually tune our model, I mean, to our needs, whether it is performing good or bad. So how can the actual shape of the filter can be decided? So here the shape of the filter here is 3 by 3, the one in the yellow, and the green one is the actual image. So here the shape of the filter is 3 by 3 by 1. So here we are only sliding it through one dimension or one channel, we say. So image will have, I mean, generally images will have three channels, RGB, I mean red, green and blue. So if we are going to convolve on that, then we would be having the filter shape of here 3 by 3 by 2. Okay, the depth will be 2 actually. So that is what I'm going to say. So it is always better to maintain, I mean, to maintain same as the shape as number of channels we have, the depth of the filter, I mean, the depth of the filter should be equal to the number of channels in the previous layer, in order to, since we are doing a two dimensional, I mean convolution 2D, in two dimensional convolution operation in two dimensional, we are not doing it in three dimensional. So it is always recommended to do in something like the shape of the filter would be the height and the width and the number of, the depth should be equal to the number of channels in the previous layer. So it would give very more accurate results, and it is, you know it is the only valid one for now if you are going to do with two-dimensional convolution. If it is in three-dimensional, then okay, you can do. So yes, we will be going with TensorFlow. uh, we will be just looking into classifying handwritten digits between 0 to 9, and that is what we call 10 classes: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10 classes, and then we will extend this particular model to classify 101 general categories what we see daily. Okay, so it would be fine. So we will be using TensorFlow, and remember, I will not be giving any particular intuition about TensorFlow, because I assume you people all are familiar with TensorFlow. If you are not, we will be definitely doing a session later on. Okay. Okay. So so general intuition for TensorFlow is, it just lets us to build a computational graph first and then feed the inputs to the graph so that it can run on either CPU or GPU. Also, it actually runs on C++, and we have a nice API for that Python to interacting with it at a very high level. Okay. So we will be using MNIST dataset for that. Okay, so here we just go through the code. So we just start off by importing, okay, utils load dataset and encode. Okay, we will get into this later on, and just we import TensorFlow as TF, that is fine, and we import NumPy as NP. Okay, I guess you people know what all these are. Okay, and then we load the dataset mnist_train.csv, and then we load the dataset test.csv, since we need to test and the train our model and then test on the test set. Okay, and here we are passing through the load dataset function, which is defined in the utils actually. So load dataset function is this. Actually, I have CSV files. You can see here this load dataset function actually loads that CSV file and just slices it off. The actual shape, actually the CSV file will be in this kind of format. The first column will be the label, and the remaining all 784, it is a 28 by 28 shape image, so all the 784 elements will be the actual image elements. So we are just going to return the data and the labels sliced out by the labels and the data. So, and yes, we will be one hot encoding the labels, since we need to classify them, and I'm going to categorize all of them since they are not continuous data. They are, not continuous data, continuous targets. Okay, so it would be better. And yes, it's better to convert them to float 32 and then encode one hot encode those labels. So as I have discussed before, so one hot encoding is something like, if you give in 3, it would be something like 0 0 0 1 and so on, and all are remaining are zeros, so 10 elements. So it would be 1 if the label is the actual target we are going to see. So yes, we will initialize the placeholders as this. So this is the input placeholder X. It is of shape none and 794. So none in the sense we can have any number of elements. So, and yes, the targets are any number of elements, and 10. Yes, it, since they are one hot encoded, we have 10 classes. And these are probabilities, probabilities. Yes, I will be coming to that later on. Please don't mind about these things. Okay, so let's get to the line 32 now. Okay, we just need to reshape our data set, since it just returns the data as it is. So here we are getting the data as none comma 784. Since we need to feed it through a convolutional neural network, we need to reshape each particular data, 784 elements, to 28 by 28. So we are reshaping it to 28 by 28, and remember, I'm doing it -1 because uh, the batch size or whatever, any number of samples can be there. So first dimension is number of samples, height, width, and the number of channels. This is also we can call as NHWC. none, I mean number of samples, height, width, and the number of channels. So we apply through convolution and ReLU and the pool the X image, and then the another convolution. So we will discuss it now. So actually, let's take a single sample and just go through what is actually is going on. So we are actually feeding in a single image here. So the sample, I mean the data set would be here, would be of shape 1 comma 28 comma 28 and 1. Since it is a grayscale image, it have only one channel. So 1 in the sense one sample, 28 is the height, 28 is the width, and 1 again is the number of channels. It have only one. We pass it through a 3 by 3 convolution. Since, I mean, 3 by 3 is the filter shape, and we have 32 as number of filters. Okay, number of filters we would be using is 32. Okay, and then we max pool it. I mean, and then we pass it through a activation function and then pool it to half. Remember, we pool it by 2 by 2 filter with a straight 2 again. Okay, fine. So we can have 13 by 13 filters as we have seen using this particular formula. So 28 minus 3, which is 25, okay, by 2, because the strides here we are using for the max pooling is 2. Yes, here we will be using 2, so that is totally, and finally we will be having 13, shape as 13. Okay, and then we pass it to the same, but here the actual filter shape would be again 3 by 3, and note that we have here 32 channels because our filter number of filters are 32 here. Okay, number of filters are 32. Okay, yeah, I will be sharing the files, don't mind. Okay, I will be sharing the files after the session. Okay, yes, the number of filters here are 32, so therefore we are going to have 3 by 3 by 32. Okay, I will be get into the code. I mean, you will get understand more when I get into the code, and we will be having feature maps of shape 5 by 5, and then we will have two, one affine layer and then the final classification, which is followed by a softmax. So let's go on to the code again. Okay, yes. So this is a function weight bias. It just creates a weight and a bias, that is okay, of the shape what we given here with a standard deviation of 0.1, which is okay, and also the bias. Okay, so this function actually what it does is it takes an input and it passes through a convolutional 2D operation, and then it goes through an activation of each element, and then it passes through a max pooling. Okay, so here we create the weight and biases for a single thing, for a single layer, and then we pass it through a convolution 2D. Okay, here pass it the input and the weight, here we got it, and the strides here are 1 1 1 1. So 1 is for number of samples we are going to step on. So since we are going to step on each sample, so it is will be 1. So this is the height we are going to step on, and this is the width we are going to take the step on, and this is the number of channels we are going to step on. So here I said padding as valid, so it would strip off whatever, I mean it just does the valid padding rather than something like a zero padding. So there are two options for us, valid and the same. If it is same, the output will be also in the same shape of the input, so we don't need that actually. And then we pass this the output of this convolution layer to an activation function called ReLU. ReLU is an activation function. It just returns x if x is greater than 0. Otherwise, it returns 0. So it can be something said as maximum of 0 comma x. And then we max pool the layer as we discussed before. And here you can see the kernel size is 2 by 2. The height is 2 and width is 2, which is fine. So the main important thing is here the number of strides. We are stepping 2 times height. I mean 2 steps towards height dimension, height, and 2 steps towards the width. So here, since we are doing 2 by 2 steps, the actual image will get halved. Okay, And also we are using the valid padding. Since we are using valid padding, the actual image will get halved. If it is not, then it will be the same shape where we return from here. So yes, coming back to here, yes, we pass in the X image, which is the reshaped version of the actual inputs. So here it is. We just reshaped our none comma 786 784 to number of samples to 28 by 28 image and one grayscale channel. Only one channel will be there for a grayscale image. Yes, we will be creating. Wait. Okay, we pass these particular image through and convolution, ReLU, and the max pool. So I just created this helper function in order to make it so simple. That's it. Okay, we pass this particular image and with the filter of shape 3 by 3 convolution, height and the width. So you can see 1 is the number of channels in the previous layer, what we call, and the number of filters I'm going to use here is 32. So we would be having the end output would be 32 of depth. Okay, so now we pass the output of this particular convolution layer to again another convolution layer. Yes, and this time we will be passing again the same height and the width, but the number of channels will be 32. Remember, I have said that the number of channels should be equal to the number of, number of the depth of this particular filter should be equal to the number of channels in the previous layer. Since the number of channels in the previous layer should be equal to the 32, then definitely should be 32, since we are doing a two-dimensional convolution. If you are doing three-dimensional convolution, then definitely it is up to your choice how to proceed. And now, yes, we are going to do with 32 filters again. So the end output actually will be of shape 5 by 5, as you can see here. The feature maps will be of 5 by 5, shape of 5 by 5, and it will be of 32. And since we are passing it through an affine layer or fully connected layer, uh, we need to reshape it. We need to reshape them by 5 into 5 into 32, since 5 is the height and 5 is the width and 32 is the number of channels it has in the previous layer. We are just reshaping it. And yes, we need to create the weights and the biases with corresponding to the affine layers too. Okay, and then we pass this particular convolution, reshaped convolution layer, to an affine layer. And here the activation function is the ReLU. So what we are doing here is the matrix multiplication between the output reshaped version. So convolution 2 here, the reshaped version of the actual convolution of the feature maps, and then we add it by a weight. Not add, we matrix multiply the convolution layer with a weight, and then we add it by n bias. Okay, so okay, and we add a dropout layer here. Okay, don't worry, I will explain the dropout in later on. So just forget about this dropout for now. And then we again pass the output. We come here in the first affine layer to another affine layer, and since we are we are classifying 10 images, 0 to 9 is 10, so we need to have the final layer of shape 10. So here it is, the weights will be of shape 128 to 10, because we just reshaped to, we just initiated the weights as 128. Okay, so yes, we will be having this particular thing, and we just pass in through in softmax. The predictions will be a softmax. So we apply softmax in order to have a probability sum up to 1. So that is the thing. And yes, we will define our cost function here. Softmax cross entropy with logits, tensorflow dot n dot softmax cross entropy with logits. And yes, we are defining the actual logics, the actual outputs we get here, the actual outputs we get here to the actual labels. Why is something that this placeholder holds. We will feed it to the later on. Yes, and yes, the optimizer I am going to here use is Atom optimizer, which is an hybrid version of RMS prop optimizer and ADA delta optimizer. Okay, it seems to be perform well when I have experimented with lots of optimizers then. And yes, we need to minimize the cost. So here I defined a correct prediction function. It just it just predicts whether the actual predicted one and the target are equal or not. Okay. And yes, in order to get the accuracy, we are just reducing the mean. You just cast the correct predictions, that's it. So if you are going to get 5 correct predictions in 10, then the accuracy would be 50, right? So 5 by 10, 1 by 2, and again 0.5, that is 50. So that is thing. So in TensorFlow, we need to initialize all our variables first in order to before actual feeding the inputs to the session. So we are initializing all our variables. So it's better to use global variable initializer rather than initialize all variables. So we will be getting an deprecation warning. That's not a problem here. And here we are doing with the batch size of 128. Since we are not going to pass each and every number of samples, total number of samples into each iteration, because at the same time, since we are doing mini batch gradient descent, so it would be fine. Yes, here this particular statement is just creates a mini batches, so nothing to explain here. And yes, here we just run the session, the actual train op. Here it is, the actual training operation, Adam optimizer, and we need to minimize the cost at each iteration. We pass it through. Yes, the start and then values are from this particular for loop. This is just creates a batch numbers, nothing like that. Batch start and the batch end. So yeah, just starting and ending. That is okay. So okay, key probability. I will get into this. Okay, wait. So I'm creating a test indices and then getting the test data, getting the test labels, and then again passing through the session. So in TensorFlow, if you are going to run any particular function, we need to run it, pass it through a session.run, and the session is initialized here with tf.session as session, because going to run one or more, I mean two or more actual TensorFlow sessions, the variables between different sessions should not collide. So that is the concept here. So yes, we are going to get the accuracy and the cost, and we are printing at each iteration. Okay, so that is the thing. So coming back to the dropout. Dropout is some kind of a regularizer we are using here. It just cancels the number of nodes, actually fully connected nodes. Instead of fully connected nodes, we can actually take out the nodes, some particular probable nodes. Okay, if you have 100 nodes, then we can take out 30% of the nodes by giving in key probability as 0.7. We just going to keep 70% of the nodes active, and we are disconnecting the remaining 30% of the nodes in order to prevent our model from overfitting. That is the thing. So it, here, this is what we initialized here, the dropout, actual dropout layer here. And then keep in mind, we always need to keep the we always need all all nodes to be connected in the testing phase. Probably in the training phase you can vary as much as here. I am keeping the creep probability 1 as 50% of the nodes are connected, and again 50% of the nodes are randomly disconnected, and here 75% of the nodes are randomly connected and 25% are disconnected at each iteration, which is fine. So yes, after running this particular model, I have got 99.2% accuracy, which is fine. Okay, and then this is okay. It would be better if you visualize what is the actual graph we have created. TensorFlow creates the operations in the graphs, so it would be better we visualize them in a graph, right? So we cannot visualize them in, at least if you visualize them, it would be something like weird if you are going to do now. So we just need to add some name scopes in order to better visualize them. So here, this is the thing. I just added some name scopes here, and here for the biases and the summaries for the biases again. So summary histograms, again names goes for convolution, ReLU, and max polling, and again yes, We are just adding the name scopes here, nothing more than that. Just to name this particular whatever comes under here, it should be in the convolution box. Some think of this as like a black box containing all the operations that are going to be done in convolution 2D operation. So something like that. And we just initialize our writer, and I'm going to write our summarize to logs and train one, and the test writer to the logs of the testing to test one folder. So that is fine. So let's visualize them. Con relu pool. Okay, wait.